Video 9 will be mainly on section 2.7 in your text. Most of the topics we're going to cover are ones that you've seen actually more in elementary, middle school than you did in high school, but we need to bring back these ideas of numbers. We're going to be looking at the real numbers. The real numbers is the set of numbers, the largest set of numbers that most of you have considered. It's all decimal numbers. Some are rational and some are irrational, and we want to go through those definitions in this section. The real numbers are all decimal numbers, and they correspond to points of a line. Every point corresponds to a real number, and every decimal number corresponds to a point. Now, just to review, a point and a line are really undefined terms in geometry. A point on that line has no dimension. It has no width, no length, no height. It has no size. And the line has no width or height. It only has length. So it's kind of abstract. If a point has no size, then when I put a point on here, if I mark a point and let's say call it 1, that mark that I made has width. You can see it. But a point you really can't see. A point has no size at all. And so they don't take up any room on the line. And yet all of the points together make up the line. And each point corresponds to a real number. Once I decide where to mark 1, if I draw a number line like this and I put 0 on and I put 1 on, then all other points are determined, right? Because once I put 1 here, then I know 2 has to be there, and 3 is here, and this might be 2.5, and -1, and -2. All of the points, all of the coordinates of points, the numbers, now correspond to a point on the line. Once I have put the unit length, once I've determined that. Okay, so let's say that we want to find the point corresponding to the real number 1.345. Well, the first thing we might notice is that it is certainly between 1, so I'm going to mark this 1 and this 2. It's between 1 and 2, and this is divided into 10 little segments of equal length. So this is 1.1 here, and this is 1.2, and 1 3/10, and 1 4/10, and 1.5, etc. And we know that 1.34 will be somewhere in here, somewhere in this between 1.3 and 1.4. So let me zoom out and we'll call this 1.3. We're just zooming in here. And we're taking a closer look, and let's call this 1.4. And we have divided that into 10 little equal length sub-segments. And so we have 1.31, 1.32, 1.33, etc. 1.34 and 1.35. Well, I can see that my number 1.345 lies between these two. Lies between these two numbers, 1.34, 1.35. So I zoom out again. And now this point down here I'll call 1.34, and this one 1.35, and divide that into 10 equal little pieces, and then this becomes 1.34 is here, and this is 1.341, and so on, 1.342, 1.345, 43, 1.344, and here we are, right here. So I could put the dot right here and this is 1.345. But now back on our original line up there at the top, I don't know exactly how to put it in up here. It's between 1.3 and 1.4, and let's see, it's a little less than, I don't know, maybe I'd put it about right here. So the point would be approximately here, and we would have seen that to begin with. But if you can keep zooming out and zooming in and zooming in and zooming in, you can make it more exact. So since points have no size at all, there's infinitely many points between two given points. And so we see there are, between any two real numbers, between any two decimal numbers, there are infinitely many more of them. So here's a question we might see in the future. Write an infinite sequence of numbers, all of which are between 0 and 1. So they're greater than 0 and less than 1. Well, there's many that we could do. Let's say this is 0 and this is 1 here. So first I'll show you how I could pick them. How about pick the one in the middle? That would be 1/2. And then I could pick half of that, which would be half of a half, or 1/2 squared, 1/4. And then I could take half of that, which would be 1/8. And half of that is 1/16, and so on. And we're just getting closer and closer to 0, aren't we? But we never get there. So here's the sequence that I got doing that: 1/2, 1/4, 1/8, 1/16, and in fact, in general, 1/2 to the n power. And it goes forever. Even 1/2 to the 50th is extremely close to 0. Too close for us to see. If we tried to plot the point, it would look like it was 0. But it isn't, and there's infinitely many more numbers smaller than that, but bigger than 0. Well, let's do another one. How about, let's call this 0 and 1 again. We're looking for an infinite sequence between 0 and 1. Why don't we do 1/2 first again? You could do many different examples. And then let's take 1/3. So 1/3. And then how about a 1/4? 1/4. 1/4. And then 1/5. 1/5. And you see what we're doing. We're getting closer and closer and closer to 0, but we never get there. 1/5. ... And in general, we could call this sequence 1/n. N equals 2, 3, 4, 5, 6, etc. So there's another infinite sequence of numbers that are between 0 and 1. And in fact, there's infinitely many sequences you could come up with. But those are just two. Real numbers are either rational or irrational. And first we're going to define what is a rational number. It has two definitions. One is that it is a real number, of course, a decimal number that can be expressed as the quotient of two integers. It can be expressed as a fraction. For example, we know that 0.5 is a decimal number and it's equal to 1/2. Or we could take 101/23. Any of these, minus 1/3. These are all written as fractions, and they also could be written as in decimal form. But any number that can be expressed as the quotient of two integers is rational. Another definition is it is a real number that has a terminating or repeating decimal expansion. Now by terminating, I mean something like 1.5. It repeats. If you wanted to call it a repeating decimal, you could. You could say it's 1.50000, and it repeats zeros forever. But we don't usually write it like that. We'll just call it 1.5. In Chapter 3, however, we will be thinking of 1.5 as having infinitely many digits. After the 5, though, they're all equal to 0. How about the number, well, 1.0123, 123, 123, ... Now the ... means that the 1, 2, 3 continues. Another way you can write that, if you wish, is 0.123, and you put a bar over the repeating part. This is a repeating decimal. And if it is then rational, we should be able to change it into a fraction, and we should be able to change fractions into their decimal form. Every fraction will either be a repeating decimal or it will just terminate, in other words, repeat zeros. Okay, so first we're going to see how to change fractions to decimals. You can always check your answer on the calculator, but remember your calculator will never give you an infinitely repeating decimal. It's going to round up or cut it off at some point. So, well, the easiest kind I didn't put down here, so let me, the easiest kind of fraction is one that has a power of 10 in the denominator. For example, 31 over 100. Well, when you divide by a power of 10, you're dividing here by 10 squared. You're going to move the decimal point to the left in the numerator. Move the decimal point 2 places to the left. So we have 31, and the decimal point, of course, is after the 1. You don't write that there. And move it 2 places to the left. So we have 0.31, or some people write 0.31. If you had 762 over 1 with 3 zeros, 10, no, let's put 4 zeros, 10,000. Well, you just take 762. The decimal point is to the right of the 2, and you're going to move it 4 places to the left. 1, 2, 3, and 4. So if you have a power of 10 in the denominator, it is very simple. You simply move the decimal point. Now for these other ones, well, let's do 6/5 next. Whoops. 6/5 I could write easily, since we have a 5 in the denominator, I could write 6 over 5 is equal to, and just multiply by 2 on the top and bottom, and I'd have 12 over 10. So if I have a 5 in the denominator, I can simply turn it into a fraction with a power of 10. That's 10 to the 1, so I'll move the decimal point in 12 1 place to the left, and I have 1.2. Another example, suppose we had 7 halves. You can divide the 2 into the 7, and you know you're going to get 3.5, but here's another way to do it. You can multiply by 5 over 5, getting 35 over 10, and then move the decimal point from the right of 5 once to the left, 3.5. So here what we've done is showed you that if you have a power of 10, in the denominator, it's very simple. You move the decimal point to the left. If you have a 5 or a 2 as the denominator, then, or powers of 5, powers of 2, you can multiply by something to get it to be powers of 10 in the denominator, and do exactly the same thing. Now you do not have to do it that way. You could use the next method that I'll do is for like 1/3. Well, here's the long way. You just take 3 and you're going to divide it using long division into 1. So the decimal point's here. 3 goes in 3. 3 times 3 is 9. And we have a remainder of 1, bring down the 0, and you see that we're going to have 10 over and over and over again. So it'll be 3, 9, 1, remainder, bring down the 0, and you see that this is going to be 0.333 repeating. So 1/3 we could say is 0.3, and one way to write repeating, I can just put a bar over the repeating part, or you can just say 0.333 dot dot dot. Now 12 over 7 is probably a little more complicated, so let's see. Let's start dividing. 7 into 12. Now again, you can use your calculator, but you may not, it may round off and you won't really know what the repeating part is. So let's go through just one example so that you can see what happens here. 7 goes into 12 once, so I get 7 with a remainder of 6. Oh, no, 7. I'm doing 12 here. Okay, so 12. I get a remainder of 5. Bring down my 0. 7 goes into 57 times. 7 times 7 is 49. I get a remainder of 1. Bring down this 0. 7 goes into 10 once. 7, I have a remainder of 3. Bring down the 0. We haven't started repeating yet. Let's see, 4 times 7 is 28, so 4 times 7, 28, remainder of 2. Bring down my 0. Oh boy, I think I'm going to run out of room. 7 goes into 20 twice. 2 times 7 is 14, and I have a remainder of 6. I still have not started repeating. So we keep going, bring down 0. 7 times 8 is 56. It goes in 8 times, subtract, we get a remainder of 4. Bring down the 0. Well, now how long is this going to last? I mean, when are we going to get a repeating part? To see this, let's circle the remainders that we have here. First we had a remainder of 5, then we got a remainder of 1, then we had a remainder of 3, and then a remainder of 2, a remainder of 6, a remainder of 4. As soon as we repeat a remainder, it's going to start to repeat. Well, think of this. If you're dividing by 7, how many remainders can you possibly get? If you divide by 7 and it doesn't go in evenly, you only have 6 remainders. You have 1, 2, 3, 4, 5, 6. That's all. So we're going to start to repeat soon. And watch how it happens. Okay, so 7 goes into 40. 7 times 5 is 35. So 35, remainder of 5. Ah, here we are. This remainder goes all the way back up here, and we have now repeated a remainder. So when I bring down my 0, it's going to go in 7, and I'm going to get 7, 1, 4, 2, 8, 5, etc. It's going to repeat. And I knew that if 7 was my denominator, that it would repeat after 1, 2, 3, 4, 5, or 6 divisions. So our answer is 12 sevenths is equal to 1.714285. Now, most of the time, you'll be able to tell this using your calculator, but I want you to be able to go through a couple of examples like this so that you really see what's happening.